My name is Kristen Accardi. I'm a software engineer working on the security team, and specifically, I'm working on Linux kernel hardening. So today, I'm going to talk with you about a project that I've been working on now for over a year, and it's still a work in progress. Code has not yet been, it's not good enough to go upstream yet or even be talked about upstream yet, but I wanted to share it with you guys because it's something that I think that is a bit radical as far as a departure from how things normally look, and so I want people to get used to it and also give me your comments and feedback because it's also a lot of stuff that I personally was never an expert in, and I'm still learning about. So I appreciate anything that you can provide me as far as feedback. I wanted to let you guys know that you can interrupt me during this talk if you have questions. It's okay to hold it till the end if you feel like it, but if you see something and I'm not explaining it clearly or you have a question or a comment on it, please feel free to interrupt me. It's perfectly fine.
Okay. Talk really loud or go to a microphone.
Yes.
Because this is all being recorded.
Right, so we are being recorded. Okay, so I'm going to spend some time first talking about why we are doing this. And then I'm going to go through some background information that was personally important to me in order to understand the problem space. We're going to talk about how we do things today, and then finally we're going to get to how I'm proposing we change things. We had all these practice sessions for this talk leading up to OSTS, and the last one I gave, the guy's like, you spent 15 minutes before you even got to what you're talking about. And I'm sorry about that, but I'm afraid there's a lot of background information that if I just jumped into what I was doing, you wouldn't understand. So. Or at least maybe one of you would, but probably not most of you. But the first thing I want to talk about is monoculture, okay? So yes, yet again, I'm talking about diversity at this conference. Only right now what I'm talking about is diversity in compute systems. So I think we're all familiar with the concept of monoculture in agriculture, where basically, you plant an entire, country's worth of agriculture in one particular species, and then a virus comes and attack it, and then next thing you know, you have the Irish potato famine. Okay, so the idea is that viruses spread very rapidly in a monoculture. And the same is true in computing. The Morris worm, for example, was able to be spread as quickly and as far-reaching as it was because everybody was basically using the same computing stack. So it was very easy to exploit a single vulnerability and spread yourself across all of the computers that were on the internet at that time. Okay, so there has been a lot of research on how to add diversity to software stacks. In fact, I wanted to show you this. This is only 6 of gazillions of papers that have been written about this. And the oldest paper on this list is actually from the 90s. And the newest one is from just last year. So there's been a lot of academic focus on here, and it continues to be an area where people are putting in a lot of research. But in reality, there's only been one method that's been adopted in practice, and that's address space layout randomization. And we're going to talk about that later. But before we do, there's a little bit of a basic concept I want to explain to you, and this is ELF. So ELF is the file format that is used on Linux systems. It is basically a specification that describes what a file should look like. It's got a header, it's got a table that points to different what they call segments, and each of these segments is what contains your code, your data, and symbols, etc. And so it has, on the highest level, it has kind of 2 formats that we care about. It's got an executable format, and it's got what they call a relocatable object format. So this is just, a sample. It's not a real diagram of what a real file would look like. And since we're talking about the kernel today, I got to tell you the kernel looks nothing like this. It's got a lot more stuff, but the important part for our discussion is that the code that the kernel is actually executing is contained in the text section. So that's what we're actually focused on protecting, is the kernel code. And that's where today the existing address space randomization occurs for the code. So the other thing I want you to understand is there's different levels of randomization. So I tried to draw this sort of as a smallest to largest kind of thing. So at the very, very smallest level, you can randomize at the instruction. So for example, especially with x86, there's multiple ways to do the same thing. So let's say you took a binary and you saw that everywhere they did an instruction one way, you could just blindly replace that with another instruction. Well, guess what? You just introduced code diversity, because now your binary no longer looks the same. You can also do this at the basic block level. I mean, we know that computers do this all the time. They reorder execution in order to make things more effective. So you can do that also in software as long as your basic blocks don't depend on each other. Again, requires compiler changes. You can do things at the function level, which we do have some plugins, I believe, in GCC that might do this. Basically, what this does is function permutation, for example, where you might add extra stuff to the end of a function definition in order to make it, that's not really used, but it makes the function signature look different, that sort of thing. And then finally, you can do things at the program level. At the program level, we can do things like function reordering, similar to basic block reordering. We can do base address randomization, which is exactly what is implemented today. Okay, the next thing is, when do we randomize? So I sort of divided this up into where the randomization occurs. So you can randomize at compile time, or you can randomize at other places. And so really the distinction here is who owns the location of where you're doing randomization. So there's things that happen. This is sort of a simplified software lifecycle, okay? So there's things that are owned by the vendor, and there's things that are owned, parts of this process are owned by the user. So the vendor will implement the code, they'll build it, they'll distribute it. The user will install it, load it, execute it, and hopefully update it. So the line drawn here is where's the control, okay? The vendors obviously are controlled by the distributor of the software, and the other part is controlled by the user. So the existing implementation, and we're going to talk about kernel, but this is also implemented in user space, but specifically kernel, the base address randomization is a program level randomization. We do have some other plugins for GCC that are part of the kernel. We have structure randomization, where you can reorder the fields of a structure. And Elena is going to talk to you after this, actually, about stack layout randomization. So hopefully you guys are all excited to see that talk as well. But these are program level randomizations. So KASLR is right here in the software process. It's executed on the user system at load time. And this makes it really easy because if you're a vendor, doing randomization at the build or implementation or distribution phase is very expensive. So by pushing that off down to the user, it saves the vendor from having to create all of these multiple instances of binaries. So here's how it works today. You have basically a fixed range from where the kernel can be loaded in memory. And there's our text section. That's all of our code that needs to be executed. And it's the memory range where the kernel can be loaded is larger than the size of the kernel text itself. And so what you can do is at boot time, you can slide that code section up and down between that memory range. And so the exact location is determined at boot. Attackers won't know the exact address of some prime piece of kernel real estate they're looking for unless they have time to be on the host system and discover it. So why is this important? It's because this is an example of how people build exploits. So attackers will use a multi-step process in order to break into your system, and it often looks like this. First, they find the address of something, And then they'll find a vulnerability that they care about, like, for example, commit creds, where you might want to use this in order to elevate your privileges. They'll find some vulnerability or bug that lets them, that they can then exploit, and then they'll cause a jump to that shell code. And so finding useful addresses is usually step one. And if you have randomization applied in there, you've just added another step to this entire process. So now step one, instead of, I just looked this up and I took my Ubuntu kernel or whatever and I figured out what the address of the thing I want to go get is, now I have to go find it on the host system first. So this is pretty good. But unfortunately, it's a little bit weak. It's better than nothing for sure, but the reality is there's only so many slots that that kernel text can fit into within that fixed range. And so that's an issue. Like, if it's what we call entropy. There's only so many, there's only so much randomness you can get with that. The other issue is that if you have a single info leak, you can calculate the offset to wherever the kernel was. So what's an info leak? An info leak is basically any time that you accidentally expose an address in the kernel. And this can happen in a number of ways, from really dumb things, like I printed a pointer out into the dmessage log, or to sort of more advanced things, like I have a side channel attack that lets me figure out what a kernel address is. Okay, so info leaks, the reality is they happen all the time. In fact, I was on my system the other day and I saw a stack dump get dumped to my dmessage log, which my distro has made it possible for unprivileged users to just read the dmessage log. And I'm like, oh, look, I'm an unprivileged user and I can look at this stack dump. Yay. Shows me all the addresses I need to know because I see the registers that are there. But anyway, so yeah, info leaks are a fact of life. So at this point, you might be wondering, okay, ASLR is really weak. We have all this decades of research on how we can do better. Then why don't we do more than what we have today? And so the issue is that monoculture has its benefits. For one thing, like I mentioned before, it's so much easier to distribute a single binary than to expect some distro to somehow have you download a random binary. For another thing, our entire code infrastructure is built around knowing that we can have a single binary, that you can check it to make sure it's the binary you expect. That, in addition, we have all this debugging and error reporting infrastructure that relies on this. We have tracing, we have live patching. All of these things rely on a consistent binary. In addition, there's this load or runtime overhead when you try to do randomization. And some people won't care about that because they care more about security than about performance, but it really will depend, how bad it is depends on where you apply the randomization. You know, for something like ASLR that's applied once at boot time, it's like, oh, whatever. But let's say now you want to do this all the time because you want harder randomization. You know, maybe you decided that you want to randomize every 10 seconds or something. You know, that's kind of unworkable. So some of these academic proposals are not very useful in the real world. Okay, so now, see, that only took me 4 minutes. We're on to the actual proposal. So like I mentioned, this is a work in progress, and it's going to be a long road to travel, although the more I do this work, the more I realize that it's not as hard as I thought it was going to be. The hard part was really understanding how to do it, and I'm still working on that part. But as far as like number of lines of code it has taken me to get to where I am today, it's not that much. Okay, so you start thinking about how can I do a better job? The first question to ask yourself is, when are you going to do the randomization, okay? So there's obvious advantages to doing it at load time. You know, everybody likes that. Distros don't have to worry about it. But at the same time, if we want to do more finer-grained randomization, we do need to add a little bit more information so that at load time we can do some of this stuff. So there's this notion of sort of hybrid vendor user responsibility for this. So what I've started here with my approach is we're going to do some things at build time to add a little bit of extra information to the binary, and then we're going to use that information at load time. So a vendor will still distribute a single binary. You can still check it, you can code with your code signing method, but it will give us enough information so that we can do more than just slide the entire binary up and down. The downside of this, of course, is all that the extra metadata is going to increase the size, but such is life. Okay, so the next question that we had to answer was what level of randomization are we going to do? So we decided to stick with program level randomization. Some of those other smaller randomization techniques do give you better entropy, but we're not trying to solve world hunger in one fell swoop. We're going to start with increments, and so we're going to stick with program level randomization. We're just going to do a different kind. So we're going to initially target modules, which is what I've done, although in this presentation I'm going to show you how you can do the same technique to the rest of the kernel. And one of the advantages of starting with, actually the big advantage of starting with modules is modules are already relocatable objects, and I'm going to talk a little bit about why that's important. And so what we're doing is we're doing function reordering. Function reordering, as I mentioned, is where you can just rearrange the functions inside your binary. The order of the functions doesn't matter as far as how they're laid out. It doesn't matter where they are. You're still calling them in the same order. So we can rearrange them. That way your binary is technically different, and where it's loaded in memory is going to be different, but you're still executing in the same order. So that's easy to do, luckily, with GCC, because GCC already has this concept of being able to spread your functions out into multiple text sections. So what does that look like? Okay, so on that right side, you see the relocatable format. It's basically exactly the same as an executable format, except there's a little bit of extra information in there. And those are those special .rel sections that you see there. Those contain a list of relocations that are normally applied by the linker at link time. And so what happens is, of course, you take all of your relocatable objects and you combine them together into a single executable. Well, kernel modules are still relocatable objects. They never turn into actual executables. So they all have the relocation information still attached to them. So when you apply the GCC flag in order to separate your functions into their own individual text section, you get something like what's on the left. And there you can see you still have a single text section, but it's empty in this case. There's nothing in it. And you have each function in your kernel module split out into its own text section. So let's take a simple module. This module doesn't really do anything, but just so that you know what the function names look like, here's what we're working with here. It's only got 2 functions. And so what we've done is we've split it into each function now is split into its own text section. There's a utility where you can spit out the ELF sections yourself if you want to play with this. And so what I've done is I've told readelf, show me all the sections after I've used this flag, and it's split everything out. You can see the top section, which used to be our combined text section, is now size 0, and all the others have a size, and they also have an offset. If you look, the text section offset is 64, but my first function is also offset 64, so it starts at the same place. Okay, so we can use obj dump to take a look at this function. We're taking a look at my test module work queue function, and you can see that, and this is what a relocatable object would look like if you were making a normal executable. This is what a kernel module looks like before you load it into the kernel. The address of certain things is left 0. So normally the linker would go ahead and resolve that based on the relocation information that you provided it. And so prior to you loading this kernel into this module into the kernel, all of these addresses of the different things that it cares about is still set to 0. So you can see it's really easy. Actually, let me go back to that. You can see how easy it would be to just put whatever you wanted there. I mean, like if you had control over the linker, if you were not using kernel module, or if you had control over the loader, which we are, we can put whatever we want there. Okay, so when you load up a module, this is what it looks like in memory. You have this, these two sections. You have this core section and this init section. The init section is only for the very beginning. When you load up the module, it gets tossed out after that, so we don't care about it. But the core section is really what we care about, and it has these things in it. It's got this stuff that's for executing, stuff that's just for reading, and stuff for writing, and everything else. So the thing that we care about here is the executable section. As long as we keep our changes within this section, our code should work just fine. Okay, so this is what it would look like. Within this text section, you're going to have, instead of a single text, you're going to have all of your functions in whatever order you decide to put it in. Okay, so that's pretty straightforward, actually. The amount of code needed to do this for modules was ridiculously small. And it's been tested. It works. John, please use a microphone.
I'm going to ask it now, but I think you probably will cover this later.
I'll let you know.
Debugging?
Debugging.
Well, debugging if you've reordered the location of text sections. So if I have a splat that splats over memory or something, right? The problem we have with distro kernels already is, debugging at scale is a huge challenge, right? But I guess with ASLR, at least you sort of say, well, it moved as a whole unit. But I could see, by the way, I think this is a great idea. But I could see a challenge if you're trying to debug at scale where you never quite get the same behavior twice.
It is a challenge, and that is something that everybody brings up when we talk about this. What about debugging? Yeah, so yes, you answered the obvious, you asked the obvious question, and I wish I could tell you that I have a slide at the end in which I'm going to explain how we solve this problem.
The debugger to resolve it, it's easy.
So there's one thing I can tell you about debugging. Okay, there's some part of this that will be solvable. For example, if you had a seed for your randomization that you could somehow pull out, then you would be able to de-randomize in order to print out or spit out your dump or any kind of trace that you need to do. So that part, I think, is solvable. Live debugging with GDB, I think, is going to be something that I would have to take a look at, and quite frankly, I haven't gotten that far along in my implementation. I've been just kind of like debugging. Perhaps I'll get there. So I think what will happen, my gut tells me, is there are going to be stuff like, for example, I have currently had to just turn off ftrace. I can't use it. Anything that's going to rely on being able to pick through the kernel binary in order to find addresses is not going to work. If instead they checked the symbol table inside the kernel, then it would work. So it'll really depend on what the tool is. And there was a question about performance. That is true that there will be a performance hit at load time. Oh, performance variability because you might be jumping, a little bit instead of a lot. It's possible, although I have a hard time believing if, like, the model was, we're staying within the existing memory footprint of the executable section. So it's not like all of a sudden you're going to have one function that's way over here and one that's way over there. I mean, they're still all within the same contiguous area as it was before.
I see like 5% variability just by swapping the order of two object files. Because it always gets worse. You never know.
It could be, yeah. Quite frankly, performance is like the last of my worries right now. All right. Okay, so modules is one thing. How do we do this on the rest of the kernel? So The good news is this. There's a lot of information already in the kernel to support the existing relocation and KASLR implementations. So, for example, I took my little module and I built it into the kernel. I applied my GCC flag to my make file, and sure enough, I use ReadElf to take a look at the program headers, which is different. You don't get these on relocatable objects, they only show up on the executable. And so I was concerned, oh no, my individual sections are going to get blown away, because they do in user space, but they don't on the kernel. So they've tacked it on to the end of the text section. There's my sections. And, oops. And the good news is, the kernel also retains the section headers, so I can get the boundaries of these functions very easily as well. So I know where I see that the information is there. I see that I know where these functions start and where they end. So now it's just a matter of handling the relocations. So what would this look like today? What is the goal? So I showed you this picture earlier. Here is KASLR. It's shoved its text section somewhere in between this range. So what are we going to do? This is what we're trying to do here. So on here, you'll notice I have this drawing in which I've retained a single .text section. Why did I do that? Because I was scared, and I thought, surely there's code that cares about alignment, or surely there's assumptions inside the kernel of order of things. There must be. I haven't found them yet, but this is what I've drawn because I just can't believe that I would be able to randomize everything. So, so I'm going with this assumption that we're going to have a text section that looks just like the other one, but then there will be stuff in the kernel where it doesn't matter. So, you know, an individual subsystem maintainer might be able to look at what the code that they have and say, oh yeah, this section could be randomized, and they'll have a make file for that. They'll use the function sections there, and then we'll get our individual text sections there that we can reorder. So it's also kind of a cop-out for subsystem maintainers who are concerned about performance and might be like, no, don't touch my stuff. You know, so, so that's what I'm going to do. So we'll have a non-randomized and a randomized area. Okay, so I mentioned that the last thing that we have to do is deal with relocations. When I first started working on this, I took a look at the VM Linux binary, and I was all excited because I was like, look, there's the relocation sections. I'm so lucky. But no, I'm not lucky. As it turns out, those sections are stripped off when you make your compressed binary because we don't need all of that information, and we're trying to only save the minimum amount possible. But the good news is, because KASLR already requires that you have access to those relocations, I can use the same information in theory, that they use. And like the way it works today is there's a table that gets tacked onto at the end of your compressed binary. And the way that the kernel boots up is there's this, I always don't use the right words. I make up words for these things. But I call the first kernel stubby, okay? So there's the stubby kernel, and he doesn't do a lot. He doesn't know how to do very much, but he does know how to uncompress the kernel. You know, he has some really basic functionality in there. They can do a little bit of memory management, and it knows basically just enough to blow up the entire kernel and slide it back and forth between its existing range. And what it does is at the end of this compressed kernel, there's this little table, and it's just a table of pointer to integers, and it's got a pointer to an address that was in a relocation section that's going to need to be shuffled. So if the kernel's moving up and down here, you've got some delta, you need to tack onto this address, and then you can update it and you're good to go. So this is what it looks like right now. Okay, like let's say one of those addresses is in one of our randomized functions that we want to move around. What will it look like? Okay, so you moved your .text.func and now all of a sudden your table is totally pointing to the wrong place. You have to keep track of where did you move it to for each individual section, so that's going to need to be fixed. In addition, oops, I thought I had a better drawing than that. Okay, in addition, we have this old address, right? The old address may have been pointing to a different text function that you just moved somewhere else. So not only do you need to take a look at the pointers of integers to places that needed to be updated, you need to take a look at what was it actually updating. What was the address that it was adding that delta onto? So we're going to have to change that too. So after all that, you may be asking yourself, is this really worth it? Although I'll tell you, again, the amount of code that it's taken me so far to start working on this, and I'm working with the relocations right now, has been very little. It's actually not that hard to do. So it isn't adding a ton of complexity, but still we like to know, how effective is something. And the answer is it really depends. It's going to depend inherently on the number of things that were actually randomized. If you take my test module with 2 functions, and you reorder the functions, you're going to have a 50% chance still of being able to guess where it was because, it's not very many functions. So it's going to depend on the number of functions. Like I mentioned, it's also just not as strong. Function reordering is not as strong a technique as some of these other things like basic block reordering. But we're trying to take baby steps here, and we're also trying to not be one of those people that lets the the pursuit of perfection stand in the way of progress. So I think this is a technique that can be expanded over time as we work on this. So, our first goal will be, let's do better than we do today. And then maybe tomorrow we'll be like, oh, let's do something different. The other thing you might be asking yourself, especially if you're kind of remotely familiar with some recent security research, is you might be asking yourself about something like JIT-ROP. So JIT-ROP is basically, it's not super new, actually. I think it's been around for a decade or something like that. But it's a way for an attacker who has access to a host machine to be able to basically read a page in memory and then on the fly create a ROP chain in order to do something. So they don't even need to be able to disassemble your binary offline. They have very nice little SDKs and stuff for this that you can go and install on the system. And then as a user, all you have to do is get yourself a page of memory and you can construct whatever attack you want out of that. You don't need to know where anything is. And so if you find a page of kernel memory, you're all set. So yeah, that's true. This isn't going to help when you have that. But if you combine it with execute-only memory, then all of a sudden we're looking at a very strong defense against code reuse attacks. So this is why our group right now is not only working on doing finer-grained kernel randomization, we're also working on an implementation for execute-only memory. We're very close to having a POC for this. And I won't have time to go into the details of the implementation on that, but hopefully you'll see a POC posted on that pretty soon. I will tell you this, though, because of the way Intel architecture is, ARM has support for execute-only memory in its architecture. Intel does not, but they do if you're in a virtual machine. So it'll be for virtual machines. Okay, so how did we do? Are we retaining the benefits of monoculture while trying to do better than we do today? And like I said, I still have a lot of question marks on this list. I mean, obviously, we're keeping ease of distribution code signing. We know there's going to be some overhead at load time for sure, at runtime. So we'll see. Like I said about debugging and error reporting, it's going to depend. It'll depend if they expect to have access to the binary and make all their stuff then. Live patching is one that I had a lot of question about in the beginning, but there was a guy, I'm sorry that I forgot his name, but he works at Red Hat, and I gave this talk at Plumbers, only it was specific to modules then, and he came and talked to me afterwards, pulled my code, tried it out. I guess he's the live patch maintainer. And he tried it out, and it worked just fine. In fact, he's very excited for my code because the same things that I need in order to do this randomization, he needs in order to do live patching. So it was like a mutually beneficial situation for a while. I'm sure he'd love it if I could hurry up and finish. But tracing, I can confirm, is totally broken. And I haven't bothered to do anything but turn it off at this point. Okay, so if you're very excited to learn more about code diversity, about some of the academic research that's going on, I've given you just a few papers to take a look at. The one paper in particular that I think if you're like all excited to go out and read academic papers, you should read the self-rando paper, because this was really my inspiration. When I read this one, I suddenly realized that it was possible. And the self-rando project was one where they did function reordering, and they took a Chrome browser, I think, or Tor browser, that's right, Tor, they did it for the Tor project. And so it's actually deployed in real life, and they're somehow managing to use it. And these browsers are very large, complex pieces of code. So they've managed to apply function reordering to the Tor browser, and people still use it. So therefore, it must be possible for us. And in some sense, we're actually luckier than they are, because they were working in user space where they don't have a loader that they can just go and mess with like we do in the kernel. Like, we can change anything we want there. And they were like, oh, I don't want to have users have to install special tools. Like, yeah, I don't care. I'll change what I want. You know? But anyway, you can go and you can read that paper, and you can see the possibilities there. Also, I do have a POC for the module stuff. It's, you know, it's obviously, it's just to see that it's possible. And if you have a thing, like the live patching guy did, where you're like, oh my God, that's totally going to break me, you could go try it out, confirm it, and then let me know that I totally broke you. Otherwise, I'm really hoping, I feel every day that I'm so close to being able to push something for the rest of the kernel. And so hopefully that will be coming soon.